Starting with the introduction, the purpose of the lab is to observe the motion of a free-falling slinky and how the tension force affects the motion of the bottom part of the slinky. Afterward, a model of the slinky was created. The lab followed the following steps: Step 1, data extraction; Step 2, model creation; and Step 3, observation and model comparison. The results show that the bottom of the slinky stayed stationary until the top of the slinky reached the bottom part, and the model closely mimics the observed data. Now to the model. This is the model created. The blue line represents the model, and the red line represents the observation. The first main physics idea used is velocity and momentum. Velocity is a rate of change in an object's position with respect to the amount of time passed. Momentum is the vector quantity calculated by multiplying the mass of the system by the velocity of the system. And lastly, according to Newton's second law, the change of momentum divided by the change in time equals to the net force acting on a system. Secondly, according to Newton's law of universal gravitation, gravitational force equals negative g/mm over r squared r hat. Third, according to Hooke's law, the force exerted by a spring is negative kx, in which the k is a spring constant and x is a stretch. Lastly, air resistance is proportionate to the square velocity, and that is represented by F air equals constant times v squared. Now to the experiment. A video of a slinky falling was sourced from YouTube. The system is a slinky, surrounding is everything else. Initial conditions were starting position 0 meters, initial time 0 seconds, and initial velocity 0 meters per second. Afterward, tracker was used to extract the object's position and corresponding time, which is made into a table and graph, and the height of the person, which is 1.75 meters, was used as a reference. Now to the code. GlowScript's WebV Python program was used to create a computational model that resembles the observed motion. Assumptions made were first, mass of the system 0.5 kilograms, which is the average weight of a slinky. According to the internet, the system stays stationary until 5.305 seconds, according to time stamps on tracker. And the constant for drag force is 212, which was derived by trial and error. Line 27 was changed for mass. Line 31 was changed for initial velocity. Line 34 was changed for start time. And line 47 was changed for drag coefficient. Line 56 was changed for end time. Line 60 to 62 were changed for force. Line 66 was changed for velocity. Line 68 for position. Line 85 for end time. Line 89 to 81 for force. Line 95 for velocity. And line 97 for position. This is a final computational model created. The top left shows a model of the movement of the slinky. The bottom left shows the position versus time graph. The top right shows a velocity versus time graph. And the bottom right shows the precise location of the slinky as time increases by 0.01 seconds at a time. This is the final graph, which was created by Excel. And the similarities are that both suggest that the system stays stationary until about 5.5 seconds and starts moving towards the negative y direction. Both have similar start and end y positions, and the difference is the model overestimates the movement of the system between 5.5 seconds to 8 seconds. Now to discussion. The possible rooms for error were in unstable recording, slinky not falling directly in the negative y direction, inaccurate clicking on tracker, bad video quality, and trial and error for drag coefficient. For my what does it mean question, I asked, why does the bottom of the slinky initially stay stationary? And the answer was the bottom of the slinky initially stays stationary since it has to wait until the top part of the slinky reaches the bottom part for the spring force, counteracting the gravitational force to disappear. For a what if question, I asked, what if there was an object with significant weight attached to the bottom of the slinky? Would it show a similar movement? And the answer is yes, it would show a similar movement. The object will remain stationary until the entire slinky has collapsed above it. And in a way, the falling slinky supports the weight of the object for a short moment. Now to conclusions. After going through the process of making observations on the free fall motion of a slinky and making a model to mimic the motion, these are the findings. The bottom of the slinky stays stationary for a moment due to spring force and gravitational force balancing each other out, and this applies even if there is an object attached to the bottom of the slinky. Thank you.